Hey there, it's Shannon MATHCHICK Myers, and today we are checking out the DISC method. So when you finish your homework, you should be able to find the volume of a solid of revolution using the DISC method, and then we'll learn about the washer method, which is just an extended version of the DISC method, and we'll find some more volumes. All right, so for the DISC method, when a region in the plane is revolved about a line, the resulting solid is a solid of revolution. And the line is called the axis of revolution. So you have something along these lines. You've got this is our axis of revolution, and the first way we're going to look at this is as if what's called your representative rectangle is attached or touching that axis of revolution. So you've got this region here, and then this width here would be W, and then this is your radius. I know it looks weird, you're thinking height of rectangle, but it's actually considered radius R. And this is our representative rectangle. Okay, so I'm going to copy this, paste it. All right, and then just erase those for the moment. So right here we said this was our representative rectangle. And over here you've got the disc it can make if you rotate it. So think about rotating this disc around. So you'll have something like this. So you have kind of like this ghost shape, right? That is the disc. Think about if it rotated around like 180 degrees, you'd be there. And so when you think about making this rotation, you basically have your disc go around something like this. Actually, kind of hard to draw, but I'm doing my best. All right, so you end up making this disc, okay? Probably more like this for our disc. A little more definition. And if you think about making kind of infinitely many discs, like imagine slicing up a tomato or slicing up a banana, that's what we're going to end up doing. So again, we have our W here, and we have, if you kind of go out here a bit, you've got your radius. So hopefully that makes a little more sense, calling it a radius. And for this one, our axis of revolution is a horizontal line. So to see how, so now I changed this around a little bit. Apologies. I went a little too quick when I was, I guess, writing this. So we're going to cross this out. So we use the volume of really infinitely many disks to find the volume of a general solid of revolution, and then that's basically by revolving the plane region that is going to be below us about, or I'm just going to say a plane region because it could be any random plane region, about the indicated axis. So if just think of the plane, or think how a plane region, or think how a representative rectangle in the plane region generates a representative disk after it is revolved about the axis of revolution. So the volume of this disk, so here, if you think of these two that we looked at initially, right, you would have the single volume of a disk where the width is kind of like the height of a right circular cylinder, right? And the radius is the radius, right? So volume of a right circular cylinder is going to be what? You remember that? So in this case, we would have volume equals pi times r squared, and then our width is the height of that cylinder. So now we're going to look at this where it's kind of inside something else, okay? So let's just make some random region, an area type region, and we're going to have it start at A and end at B. That'll be part of the bounds. And then we have, I don't know, we can have it look sort of like this. Like I said, it could be any sort of region. All right, so that'll be the outline of our region. It will also be bounded by our axis of revolution, which is here. So this is our axis of revolution. So my intent is to rotate it around there. So if we take a look at that and just kind of sketch in, so we know we're dealing with the whole region, not just the outline. We've got this situation, and then our representative rectangle can be drawn anywhere. That's what you got to remember. And think of this as sort of zoomed in, because we're going to have infinitely many of these, right? So you've got your plane region, and you've got your representative rectangle, which is now not the entire area, it's within our plane region. And now we are going to go ahead and copy this right? And then I'm going to just take a few things out of there so it doesn't look too messy. Now what we do is we make sort of like a shadow graph. Remember how we did that before? And so this one would go maybe about here, a little further up here. I'm just trying to mirror the one that was there. And then it's rotating all around, right? So you'd have this rotation here. You'd have this rotation here. Isn't that cool? Right? And so you'd make your whole, actually I think that one doesn't look so good. You'd have your whole deal going here. Sorry, that looks worse. Okay, so you'd have your, I'll just make it thinner. Okay, good. I think that's all right. All right. And then you can kind of color that in if you want, but we basically have this whole region that we've made. And it's now a volume. We've rotated this region and made it this volume. Okay. All right. So now what do we have going on? Well, if we say that this axis is not just some random axis, let's just say this axis happens to be the x-axis, the line y equals 0, right? Then this would be dx, the width of our representative rectangle, and then at any given time, the radius of our disk that we're interested in would be r in terms of x. Isn't that pretty cool? And so your volume would be, looking at it in differentials, for one disk would be equal to pi capital R at x squared dx, right? Well, let's keep it in differentials. So in differentials, you'd have delta x. We'll just make these we'll make it a regular partition. So this would be delta x. All right, and then a single disk, right, would be like this. You'd have this single disk going around to that other side, and you'd have your representative disk. So again, remember how I said like chopping up that slicing up that banana or the tomato. All right, so one disk would be this representative area, or this volume, made by the rotating the representative rectangle about the x-axis in this case. So approximating the volume of this solid by n such disks of width delta x and radius r of some xi produces the volume of the solid would be approximately the summation from I equals 1 to n of pi r squared. So our r is r at xi squared, and then we have r delta x, which, remember, you can bring out the pi. The pi is just constant, doesn't have a subscript of I on it. And then times delta x. Now, as n approaches infinity, the norm of delta approaches 0. So you're going to have the volume of the solid. And this will be even a closer approximation, will equal to the limit as the norm of delta approaches 0 of this summation from I equals 1 to n. And then we have pi times that. So we're going to take the limit of all that. And then you have your r at xi, that whole thing squared, times delta x. And then you can bring the pi to the front. And as the norm of delta approaches 0, n will approach infinity. And then what is that? That's just the pi times the definite integral from a to b of r at x dx. And that r of x, is squared. So to put it a little bit more neatly, to find the volume of a solid of revolution with the disk method, use one of the formulas below. So we would have, let me see, I think that looked pretty good when we pasted this. So we'll have this be our shape, and then this is for a horizontal axis of revolution. I'll change this up just a little. And so here, this right here is going to be our r at x. The width of the rectangle is going to be dx. This is for a horizontal axis of revolution. And our volume will be equal to pi times the integral from a to b of r, capital R at x, squared dx. Now for a vertical axis of revolution, it's kind of cool. I'm going to use the same shape, but we'll edit it a bit, okay? All right, so our axis of revolution now is going to be vertical. The plane region, still the plane region, all right? And now instead of going from A to B, we'll be going vertically. So we'll have our axis going this way. So now this guy is the way we're rotating. And and this is our axis of revolution. And then our representative rectangle will be the other way. And then you'd be going from y equals c to y equals d, instead of having, and then this here would be our dy. And so at any given time, this whole thing here would be r at y cool. Now the way I've drawn this one, it gets more complicated. I mean, you'd have to do kind of a difference of two y functions to get that length, right? But you get kind of a general idea. So anyway, if you've got this vertical axis of rev, your volume will be pi times the integral from c to d of quantity r at y squared, and then with respect to y. Okay, so now let's take a look at some problems. So how would we do this? Finding the volume of a solid of revolution using the disk method. Now, actually this one, we're gonna skip the first one because it actually requires the washer method, so we will come back and do this guy. But this one works out great. So we'll go ahead and make a picture of our graph. We can actually do that up here. That won't change. So we've got y equals 2x squared. Now, depending on what we're rotating about, we might want to also solve for x. So let's just do that real quick. If y is 2x squared, x squared would be 1/2 times y. And then if you square root both sides, x would be plus or minus the square root of the whole quantity y over 2. But y, we're only looking at the positive side for x. So we're going to choose that positive root of y over 2. Okay, so that is where we isolate x if we need a function of y, all right? So let's just make our graph. So something like this. We have something like this. Actually, that's not that fabulous. Okay. Now, when x is 2, y is going to be 2 times 4, so that'll be up at 8. So I'm thinking that we may want to this will be 10. Okay. And then making our graph, right? We're bound by, we'll have a point at 0, 0, right? And then we'll have a point at, when x is 2, y will be 8. So about right here. And then at 1, you'd have y is 2. So it's going to look something like that. So if we go draw that up and then draw down that line, x is equal to 2, you've got your basic region that we're dealing with, right? Good so far? Okay, I'm not going to draw in the rectangle yet because it's going to change depending on what it is that we're revolving about. Cool? Okay, so I'm going to paste this on each one of these. And actually, I mean, if you have this technology, you might want to do it too, because our very last example must have really liked this function, because guess what? It's here too. Okay, so here we go. We're starting with our rotation axis being the x-axis. So we're going to rotate about this guy. And so that means, remember, that you have to kind of draw your little ghost graph. So you'd have a point if you were, you're reflecting it across that axis. It would look something like this, right? So it's really kind of groovy looking. You've got this going on, and then you've got, circle around a bit. So it looks kind of like, spinning a top. All right. And then shade it in a little bit more. Very good. Excellent. All right. I love the little pencil feature. Now, okay, so we have our picture for this. We'll fill in a few more things. This is our y-axis. And remember that y was equal to 2x squared. We were also bound by y is 0 and by x is 2. And so when we draw our representative rectangle in there, it needs to be perpendicular to the axis of revolution. So you can see the little blue representative rectangle. And so at any, given time, our r of x, right, would be, you could write it as the uppermost graph is 2x squared minus the bottommost graph, which is the graph y is 0. So r, capital R at x, is just 2x squared. Good so far? Awesome. So our volume will then just be pi integral. We're doing dx, so a to b, capital R at x squared dx. And so the volume will be pi times the integral. X goes from 0 to 2. And then our capital R at x, remember, was 2x squared. And that has to be squared from our formula. And then we're integrating with respect to x. So the volume will be pi integral 0 to 2 of 4x to the 4th dx. Integrating, we will have pi times 4/5 x to the 5th from x is 0 to x is 2. So we'll have pi, and then actually we can do that as 4/5 pi. Can bring out that 4/5, and then we'll have 2 to the 5th minus, it'll just be 0. I'll write it in for this one, 0 to the 5th. So the volume 2 to the 5th is 32. So we'll have 128 pi over 5 cubic units. Groovy? All right. Now, let's see what our next shape looks like. All right. So our next, the basis is the same, but now we're rotating this one about the line x equals 2. So the r of x is going to be a little bit tricky, right? So here is our axis of revolution. So it's vertical, right? It's the line y is 2. So we're going to have to get r of y, right? Because our representative rectangle is going to be like this. And to find out what that radius would be at any given time, we're going to have to subtract the rightmost function of y minus the leftmost function of y. So we basically have r of y equals, the rightmost function is x equals 2, right? That line, the axis of rev. So this is also our axis of revolution. And so a function of y is just like in equation form would be an x equals. So that's the rightmost. Oops. And then the leftmost, remember how we solved for x and we got the square root of y over 2, right? So that was our leftmost function. And so we'll subtract the square root of y over 2. So this one, a little bit on the mean side maybe, but doable, right? All right. And so now let's go ahead and take a look at what this will look like. So we'll have something like this for our little ghost graph, right? It'll go kind of like that after it's been revolved, and then we'll have a more defined kind of a circle here. Cool, cool. Almost like a Hershey's Kiss. A very skinny, tall one. All right, so now putting it together, this one takes a little algebra. The volume is the integral from pi times the integral from c to d of r at y, that whole thing squared, dy. So volume will be pi. Now y goes from, awesome, 0 to 8. The r at y that we found was 2 minus the square root of y over 2. that whole thing is squared. So check your algebra. You're squaring a difference of two terms here. All right, so don't forget we've got to square that whole quantity. So we'll have the integral, pi times the integral from 0 to 8. 2 squared is 4. And then we multiply 2 times the product of the ends. So that'd be 2 times 2 times root y over 2, which gives us 4 times root y over 2. And then the square root of y over 2 squared is just y over 2 dy. And continuing, we'll have pi times, now we'll integrate, we'll have 4y minus, we get 4 over the square root of 2, y to the 1/2. When you increase that power by 1, you get 3/2. So when you divide by 3/2, you can flip and multiply by 2/3, and then we'll have y to the 3/2. And then y, we'll have 1/2 times y squared over 2, which is 1/4 y squared. That's going from y is 0 to y is 8. So hopefully you can see that that lower limit of integration will be 0. So we'll have the volume is pi times 4 times 8 minus 8 over 3 root 2, and then 8 cubed, and then the square root of that. That's what raising to the 3/2 means, plus 1/4 times 8 squared. And then, like I said, the lower limit zeroes out. So the volume will be pi times 32 minus, you bring out 1/8, so we still have an 8 over 3 root 2. You bring out 1/8 from that square root, we'll get an 8. And then we have a square root of 8 left. That's what we get from the square root of 8 cubed, plus 1/4 times 64. So our volume will be pi times, when you divide 64 by 4, you get 16. You add that with the 32, we'll get 48. Now we're going to have minus 64 over 3 root 2. The square root of 8 is the square root of 4 times 2, so we're going to get 2 times root 2. Now, the root 2's divide out. When I bring a 3 out, or 1/3 out, sorry, pi over 3, I've got to balance out that 48, so I'll get 144. And then minus 128. So our volume will be pi over 3 times 16. So we'll get 16 pi over 3 cubic units for this one. Good, good? Awesome. All right, so the washer method. With the washer method, we're just, sorry about that. The washer method. The disk method can be extended to cover solids of revolutions with holes by replacing the representative disk with a representative washer. The washer is formed by revolving a rectangle about an axis, and we'll show it below. If R, little r, and big R are the inner and outer radii of the washer, respectively, and W is the width of the washer, then the volume will end up being pi big R squared minus times W minus pi times little r squared times W. But what is that? You factor out the pi on one side and the W on the other, you'll get capital R squared, so the outer radius squared, minus the inner radius squared, and then times W on the right. So what we'll do, again, is we'll take a look at a picture, right? That's always nice to do. So you've got your axis of revolution again, and then you've got your representative rectangle. This time it's floating, all right? And so this will be W, and then you'll have this big R, so the outer radius is capital R, and then you'll have this smaller r. Good so far? Okay, so let's copy this one, or redraw it, depending how you are doing this. And then we will have once you rotate this, I'll see if I can keep the so we're rotating about this axis. So you've got this smaller R, right? That's rotating around. Sorry, this is distracting. So you've got your smaller, kind of this hole that's made. Disc. Terrible drawing. All right, so let's erase some of this so our drawing will be a little neater. I don't know how neat we'll be able to manage, but okay, so you kind of have, you know, your ghost rectangle is over here, and then you're gonna make a disc here, and then that would be like that smaller one, right? So you'd have kind of this disc that was made. Sorry, I'm not the very best artist ever, but you've got this smaller boundary, I guess, of your disc, and then you've got this upper one that goes like this, right? Something like that. And that one is that upper one, so that's kind of that upper boundary. And then what's inside, you know, is how the disc rotated that volume, right? So all of this here is the one disc. So again, you'd be adding all of these up, go kind of like a tire, I guess. So you'd be adding all of these up, and what'll happen though is they're going to be inside a shape. So if you think about something like this, I mean, it could really, of course, be anything, but let's say you had a shape where the topmost graph looked like this, and then your bottommost graph maybe was just a line, right? So oops, I have to do that on the next one. All right, so then this here, you'd have, your region. So let's just make the region purple overall. That's the region of interest, and suppose that we want to rotate it about a horizontal axis. So our representative rectangle will look like this, and then you would kind of redraw your shape. So you'd have your ghost shape, right, would be something sort of like this. And then you'd have, actually it'll be, has to connect, right? It was something like that. And then you would have your rotation, right? So you would have that rotating around, right? Like this. Actually, so at our representative rectangle, you'd have something like this, right? With that rotation, representative rectangle. And then you'd have, which would make our representative disc, right? And then you'd have another one up, here. And then if you just kind of kept going, right, you'd make all of these discs. So it's going to end up looking something like this. And so it won't be solid this time, right? It'll be kind of like a bowl. Anyway, like I said, not the best artist. You've got great visuals in your book, but let's label what we got. So in this case, our little r of x would be here. Our big R of x, so the outer radius is capital R at x, would be here. And then do you see when you subtract the red volume, or the red solid from the purple, you would get what's inside, which is kind of like your bowl. Okay, so let's go ahead and take a look at, oh, and our volume, sorry, let's, our volume then would change, and it would be equal to pi times the integral a to b. Now, you would have your outer radius squared minus the inner radius squared, and then that all of that would be with respect to x if you have a horizontal axis of revolution. If you have a vertical axis of revolution, you know what you do. That's for horizontal. Or it would be integral c to d r of y, capital R at y squared minus smaller r at y squared, and then dy for vertical axis of rev. All right? Okay, so anyway, let's do this. So we're going to start with this one down here, and then we'll jump back up to the one that we did before. Now, or the part A of the problem we were doing before. So now with this guy, we're going to be rotating about the line y is 8. So we're going to extend the axis until we get to 16, because our axis of revolution is going to be this line y is 8, and that is our axis of rev. Okay, so for this one, you're going to have, remember, our little kind of ghost shape. So this is a length of 8 up here at 2, x is 2, and then maybe a point right here. Oops, sorry. So we'll have something like this. I'm making it too fat. I think it's the pencil. I'm going to go to the pen. There we go. Okay, and then we'll use the pencil just a shade. All right, good so far? And then our axis of revolution is horizontal, and so your representative triangle, or rectangle rather, is going to be like this. And then you'll have something, you know, something like this that you made. All right, so you'd have something along these lines, maybe, you know, a little shading in here. And then let's figure out what we got, okay? So now our axis is horizontal, so our rectangle is going to be perpendicular. And then it's going to be a function of x. So this would be the inner radius, r of x, is going to be equal to 8 minus 2x squared, right? Because the graph is y is 2x squared. And then the larger one is going to be eight. So the outer radius in terms of x is just going to be 8. So our volume will be the integral from a to b of, and then we have our pi, don't forget, the outer radius squared minus the inner radius squared with respect to x. So our volume will be pi. X is going from 0 to 2. And then we have r at x, the outer radius was 8. So we'll square that, minus the quantity 8 minus 2x squared squared dx. Doing your algebra, we'll have pi integral 0 to 2, 64 minus 64, and then 2 times 8 times 2x squared is going to be minus 32x squared, and then plus 4x to the 4th. And simplifying, we will have 64 minus 64 zeros out. We'll have a positive 32x squared minus 4x to the 4th dx. Integrating, we will have 32 thirds x cubed minus 4 fifths x to the 5th. That's going from x is 0 to x is 2. Again, that lower limit of integration will zero out. And so we will have, I'm going to pull, well, no, I'll plug it in first. So we'll have pi times 32 thirds times 8 minus 4 fifths times 32. So our volume will be pi. We can take out a 32 times 4 from each of those. Do you see that? So 32 times 4 is going to be 128 pi. And then I also want to bring out the 1/3 to balance that out. We have a 2 remaining, and then to get a common denominator, I think we're going to end up with a 10. And subtract from that 2. Nope, 3. So our volume will be, this is 7, of course. 8 is 56. 7 times 2 is 14. Plus 5 is 19. 896 pi over 3 cubic units. Because remember, this here was 7. Cool, cool? All right, so now let's come back here and go to number 1A. All right, so for number 1A, we want to revolve this one about the y-axis, which is the line x equals 0. So it's a vertical axis of rev. So you're going to have the representative rectangle be like that. And then you have your ghost shape, right? So your ghost shape will have something like this. All right, that went a lot better. All right, and then of course it revolves, right? So you're revolving about this axis here. And so oops, purple. Something like this. And a little shading. It's interesting, isn't it, the different solids they make? So it's almost like a drink cup. Cool, cool. All right, so when we do this one, let's figure out what we have for the inner radius. So our inner radius is just, this distance kind of here. Whoops, I went too far. This distance here. And that distance is our graph where x has been isolated, right? So these are in terms of y. So the inner radius, r of y, is going to be root y over 2. And if you want, you could say minus 0, which is just root y over 2. Now, your outer radius is going to be from the outer edge of that cup, if you will. And so that would end up being the line x is 2, right? Minus the line x is 0, which is just going to be 2. So volume will be the integral. Since it's a dy, we're going to go from 0 to 8. We still have pi multiplying. And then we have two squared minus root y over 2 squared dy. This one I think will be nicer than some of the others. So we'll have pi times the integral from 0 to 8 of 4 minus y over 2. That's so nice. Dy. So our volume will be pi times 4y minus 1/2 times y squared over 2 is going to be 1/4 y squared. And y goes from 0 to 8. Remember that lower limit of integration for these two will be 0. So we're going to have pi times 4 times 8 minus 1/4 times 8 squared minus 0. So we'll get pi times 32 minus 16, which is 16 pi cubic units. Cool, cool? All right, so that's all we have for this section. I hope you have a wonderful morning, afternoon, or evening whenever you're watching this show. And hey, if you like what I'm doing, click on that subscribe button. Maybe share the video, maybe like the video. Bye.